In section 1.4, we're going to be measuring angles and see what happens when they combine, a lot like in the last section where we did the same thing with segments. You're going to find they have pretty similar rules too. So I'm going to skip past that question at the top for now and just get right into our description of what we're going to call an angle. So an angle, and again, you can feel free to pause and get all this stuff down for our vocab, is formed by two rays with the same endpoint. So those rays are the sides of the angle, and then the endpoint is that shared vertex that's in the center. I think most important for an angle and getting used to it is naming it, so this middle section. Even towards the end of the year, people struggle with, like, especially these kind of three-letter names that we're going to see. So it is going to be good to get comfortable with naming angles and being able to identify them from a figure. So easiest way to name an angle is if I'm given its vertex. So I can name this something like angle A, and we do have notation for an angle, so kind of like a little open angle right in front of that A. Kind of like how you see that for that angle BAC as well. But besides just using just that vertex name for my angle, I could also name it using that middle method, so a point on each ray and the vertex. So I like to think of this as naming the angle as I would draw it. So angle BAC as if I was drawing the angle this way, or I could call that same angle CAB if I was to draw that the other way around. I could also name this angle rather if I'm given a number for it, which again you won't have all the time, but if I am, I could just call this something like angle 1. And if I'm trying to describe the pieces of this angle or the components, I know that again the sides are composed of those two rays, so ray AB and ray AC, and then again the vertex being that shared endpoint of those two rays, and that's going to be at A. So when I name angles using the 3 points, the vertex must go in the middle according to our rule below, and again that's why with these two names, angle A went in the center for both because that was our vertex, and again if I was to draw it, BAC or CAB, either way that's going to be in the middle of that angle because it's that shared endpoint. And besides the angle itself, we can also describe the regions around my angle. So the interior of my angle is going to be the region that's all the points between the two sides of the angle, exterior being all the points outside. I think the easiest way to think of that is like interior, exterior of like a building or a house. Interior, just thinking inside, like interior design, something like that. Exterior, you're just thinking outside your house. So same thing with an angle. If my angle is opening up and I'm describing the angle as that inside or outside, I can just use those phrases interior or exterior. So we're going to focus on naming. Oops, sorry if I blew that up a little bit. So we're going to try naming with our first couple angles here. Again, we're given numbers for these, which we won't have all the time, but we're given angle 1 and it looks like angle 2 next to it. But if we want to come up with different names for angle 1, we can call this angle a couple different things. We could call it angle JMK. We could also call that angle the other way around. So again, if I was to draw it JMK, or I could draw it as KMJ, would be another name for that same angle. So angle, if I can draw that notation, angle KMJ, noticing that M, our vertex, is in the center of both names. And if we try names that are similar for that angle next to it, again, you guys can give it a shot first and pause the video before I reveal it. But our names are going to look pretty similar. So we already used the name KML. Other two names that I could use for this would include angle 2, kind of like how we named that first one angle 1. Or I could just reverse that name, again, as we did before, and call that angle LMK. If you did try to use the name angle M by itself, that's kind of leading us into our third question. Notice that wasn't an answer to either of those two questions up above it because angle M is going to be used by really three angles that share that same vertex. So that's what I used as my description. It would not be a correct name because if I was to just use that single vertex, again, I'm not sure if angle M would be this angle that we named angle 1. I'm not sure if angle M might instead be that one that we call angle 2. Or we could describe this larger angle, this angle JML. That could also be angle M if we're not really sure which one it's going to be there. So again, can only use a single letter name when you have a case like this, when you only have one angle that uses that vertex. If there's multiple angles that share that vertex, we're not sure which one it's going to be, so we can't use that single letter name. Got to make sure we name it with that 3-letter name instead. So again, pausing if you need a little bit more of this vocab down, but just see if we can read some of this off. This is just basically how we're going to measure an angle, and that's going to be in what we call degrees. I'm sure we've heard of degrees of an angle before. Just a little bit of a notation again for indicating measure is we're just going to write a little m in front, so it looks a little bit like this. If I'm trying to say the measure of this angle A is 62 degrees. And again, notice that we actually don't put the degree symbol next to a measure. If I'm saying the measure of an angle, we're already applying it's in degrees, so I can just write 62. Technically, you don't want to put that degree sign as it would be labeled in a figure. In a figure, we can indicate degrees, but if I want to say degrees for the measure, I'm already saying that with that little m. You can read through the protractor postulate, but it's saying something a lot like our ruler postulate when we're looking at segments. And I'm going to get into the actual usage of it with this section down here. Basically, what we use this postulate for is to measure an angle, again, a lot like we use our ruler. And the measure of these angles, so in this case, angle COD, is going to be the absolute value of the difference between those real numbers paired with this ray OC and the ray OD. So again, basically just the sides of my angle. And on the protractor, just like with a ruler, we can just line that up with an actual measurement. Easiest way to measure an angle on a protractor is to line it up with one side at 0, as we're going to see in that next figure down below. Some of those angles have been lined up with that 0 side facing down. But it's still possible, just like we can kind of move a segment around on a ruler and still know its length, as long as we stick to that absolute value of the difference, which is, again, basically just finding the distance from one to the other. And there's two different ways we could find our measurements on a protractor. We could either stick with the outside measurements or we could stick with the inside measurements. As long as you keep them consistent, you're going to get the correct answer for your measurement. So the measurement that I included in my description was using the outside measures. I said take the measurement for C, which lined up with, I used the inside, which lines up, it looks like at about 135 right there. So if I took that measurement and subtracted, it looks like D. I kind of guessed. It looks like it's not an exact value, but I said about 33 or so. If I subtract those two and find the absolute value or the positive difference, I got about 102. We would also get the same answer, though, if we use the outside measurements. So if it looks like C is about 45 on, again, the outside part of this protractor, we could do the same thing with D. If that looks like it's been, again, this is kind of estimating, but let's say about like 147. If I was to subtract those two and find my positive difference, that's still going to give me that same measurement of 102. So big thing for measuring on a protractor is either measure with both outside measurements or both inside measurements. What you don't want to do is you don't want to use the inside measurement for one part of my angle and the outside measurement for the other. You're going to get those to give you an incorrect answer if you switch those up like that. So yeah, again, either 2 inside or 2 outside. Doesn't matter which one you choose, but you do need to make sure you stick consistent with either both outside or both inside. So we have angle names. Sure, a lot of you guys have seen the names of these different types of angles before if I want to classify them. Acute angle is going to be anything that measures between 0 and 90 degrees. Think of them as basically your smaller angles. A right angle is exactly 90 degrees, and no more, no less. Obtuse angles being between 90 and 180 degrees. We usually think of these as like our larger angles. And not as often that you're going to see this kind of angle, but we're going to call that a straight angle if we have an angle that essentially just forms a straight line, and we're just going to say that's 180 degrees exactly. So if I was to use that protractor to measure these different kinds of angles, I'm going to do one. Keep shrinking that. Sorry about that. I'm going to do that first one and see if you guys can do those other two. Again, just using basically the same rule. So if the first one's asking me to find the measurement of angle LKN, if I want to know where that's headed first, again, it's good to identify angles based on their name. All of these are going to use that vertex K. So again, we can't call these just angle K. But if I'm using L and N to form my sides, I drew the angle basically that we're trying to represent. So again, I could either measure with the inside measurements or the outside measurements. I'm going to stick with the inside measurements because it looks like one of them is just going to be at 0. It's going to be pretty easy to use in our calculation. So if the other side of my angle looks like it's about 145, all I have to do is just do that absolute value of my difference. Don't really have to worry too much about absolute value. Again, that's only there to make sure that my angle is going to give me a positive measurement. But yeah, if I get 145 from that just by using the inside measurements, that was 145 degrees. I'm going to say that we're already looking for the measure, so I have to put that degree sign. And we know if it's 145 degrees, that's going to make that an obtuse angle. Again, that measurement is between 90 and 180. We're thinking of those as our larger angles. So try the same thing with those next two, but I'm going to go ahead and reveal those answers right away. JKL, if I use the same measurement, again, I just stuck with, it looks like JKL, if I picture that, JKL. I use 90 and I use 35, so it looks like I stuck with the measurements on the outside. Again, you could have also done 90 for one, and then it looks like 145 for the other, and gotten the same answer. But yeah, either way, we get that measurement is under 90 degrees, which makes that acute. So again, think of your smaller angles. And if I was looking at the measurement of angle JKN, again, maybe a little bit easier to measure because we know, kind of looks like that angle from up above. This is going to form our right angle, either with the inside or the outside measurements. We could do 90 minus 0. That positive difference is 90. We could do 90 minus 180. Either way, that positive difference is 90 again. And 90 degrees is going to make that my right angle. So next, we also just define congruent angles. Again, pretty much the same thing as when we saw congruent segments. We just want to make sure a difference in the notation. We can say the measures of two angles are equal. So let's say, for example, that the measure of angle A is 20 degrees, measure of angle B is 20 degrees. We can say the measurements are equal, kind of like how we say the lengths of segments are equal, but the angles themselves we don't call equal, we call the angles congruent. So congruent would be angles, the equal part would apply to just their measures. And we can use that again forwards or backwards if I already know that the measurement of one angle here is 90. And we're going to see markings like this too. So it looks like in this figure, measurement of GHJ is 90. GHJ looks like it's the angle right here. If I'm trying to find the measurement of angle KLM, notice that they're given little markings, a lot like our congruency markings for when we had our segments. If I have, it looks like two little arcs on one and two little arcs on the other, I'm referring to these little markings on the inside. That means that those are marked as congruent angles. So if I know the angles are congruent, again, that tells me that the measures of those are also going to be equal. So I know the measure of that one that we're looking for is going to be 90. And I can just say, since those two angles, KLM, the one that we're trying to find, and the one that we already knew, that was GHJ, was already 90. We know they're congruent. Again, angles being congruent, but measures being equal, we know that if one's true, the other has to be true as well. And next question, if you're trying to pick that up, again, pretty same concept. We're just looking at two different angles there. We do want to make sure that they have the same congruency markings. It looks like one marking and one marking. So yeah, it looks like if the angles are marked congruent, I know that DEF is also just going to be 49. Again, since the angles are congruent, that's what's telling me that the measures are going to be equal. Next, we have the angle addition postulate. We're actually finishing with this, a lot like how we use the segment addition postulate in our last section. And essentially, this is kind of the same concept. Last time we just said that we could add the lengths of segments together, and that's going to equal the combined length of my larger segment. Here we're doing the same thing, but we're just doing that with angles. So again, I think sometimes this is a little bit easier to see with values. What this is saying is, again, if I add like the first smaller angle with the second smaller angle, then that's going to equal the sum of that larger angle that combines both of them. So let's say if I had, again, like 20 degrees for one and 40 degrees for the other, that just allows me to say that the larger angle is going to be 60 there. So if I'm trying to use this rule, again, we're going to get questions a lot like we saw in the last section. We're given expressions for both angles, but we're only given one value of, it looks like the largest one there. So RQT is that larger combined angle making 155. If I want to make this into a geometry expression, I know I can use that angle addition postulate to add those two smaller angles, it looks like on the interior of that largest one. And I know if I add those two smaller ones together, it should equal the sum of the larger ones. So if I add, again, RQS, SQT, or TQS rather, that's going to equal the total. So if I get those expressions down, 4x minus 20 plus 3x plus 14, again, all I'm doing is substituting the expression that I'm given for those angles. That's going to be equal to, we're told the biggest one is 155, so let's say that's 155. I get 7x minus 6, if I combine like terms, equals 155. 7x is going to be 161. If I add the 6 to both sides, and then if I divide, might have to do that one in your calculator, but I think I get 23. You do want to be careful to substitute your answer back in. We need to find the measures of the angles and not just find x here. So if I'm finding the measure of the first one, we know the first expression is 4x minus 20. So if I'm trying to find the first one, 4 times 23 minus 20, I get 92 minus 20. So I get that to be 72 degrees. I know that if the first angle is 72 degrees, we could actually take a shortcut at this point. Again, so far we've taken x and we substituted in for one. Could also substitute x in for the other expression as well, and it would be pretty easy. But another way to do this is to remember that if the entire angle is 155, 155 minus the one that we already found will tell us what's left. And that's a little bit of a faster way to find that the other measurement is going to be 83 degrees. So again, we have 72 for the first that we find the expression for, 83 degrees for one that we took the shortcut with. And we know that since they both add up to 155, that's going to be that largest total. So getting a little bit short on time, but I'm just going to reveal that final answer. We do take pretty much the same steps. Here you just need one extra piece of information. We need to know what a straight angle means. So last time we were told that the measure of the largest angle is 155. Here all we're told is that it's a straight angle, but that makes 180. And then our question's essentially the same. Add the first angle expression to the second angle expression using our angle addition postulate. We know that's equal to the total of a straight angle. So if I take the same steps, I want to make it my expression to solve for x, substitute x back in for one angle, and then once I found the first angle, we could just subtract that from the largest total, which in this case is 180. That's going to find us our angle that's left.